Hi everyone, welcome to Agnes Tech Zone. In this video, I am presenting the topic Booth's multiplication algorithm. The contents of this video are introduction, flowchart representation, algorithm, and examples. What is Booth's algorithm? Booth's algorithm is a multiplication algorithm used to multiply two signed binary numbers in 2's complement representation. It simplifies the process by reducing the number of addition and subtraction operation required during multiplication. The flowchart representation for 2's complement multiplication in Booth's algorithm. This algorithm starts with initializing the registers. First, we store the 0 value into the accumulator and q minus 1 is equal to 0. M is the multiplicand and q is the multiplier. And count is equal to n, which means multiplicand and multiplier means 4 bits means the n value is 4. Now we make decision based on the Q0 and Q minus 1 register. If the Q0 least significant bit is 0 and Q minus 1 is equal to 1 means we perform A is equal to A plus M, which means accumulator plus multiplicand. If the least significant bit of Q0 equal to 1 and Q minus 1 bit value is 0 means we perform A equal to A minus M. Otherwise, the Q0 and Q minus 1 which 1 means or 0 means we perform arithmetic shift right accumulator Q and Q minus 1 register, then decrement the count value. After that, we checks the count value is 0. When will the count value reaches 0, it end of the particular algorithm. Otherwise, again perform the same steps in an iterative manner. Steps in Booth's algorithm. First step is initialize values. So I already explained in flowchart, M is the multiplicand. If it is in binary number, if it is negative means we take the 2's complement for the given value as the multiplicand. Q is the multiplier. Here also in binary, the value is negative means we take the 2's complement. Q minus 1, a single bit register initialized to 0. A is the accumulator, it is also initialized to 0. N is the number of bits in the multiplier and multiplicand. Then we determine the action based on Q and Q minus 1. For each iteration from 0 to n minus 1, check the last bit of Q, that is least significant bit of Q and Q minus 1. If Q0 is equal to 1 and Q minus 1 is equal to 0, we subtract M from A, that is A equal to A minus M. If Q0 is equal to 0 and Q minus 1 is equal to 1, we add the value, add M to A, that is A is equal to A plus M. If Q0 value is 0 and Q minus 1 value is also 0, we didn't perform any operation. Likewise, Q0 value is equal to 1 and Q minus 1 value is also 1 means we didn't perform any operations. After that, perform the previous steps. We right shift the each bit. Shift the combined accumulator Q and Q minus 1 register right by 1 bit. In this, we maintain the sign bit in accumulator. So the MSB bit in the accumulator bit is the sign bit. Then perform the above steps 2 and 3 up to n iterations. To get the product, we combine or concatenate the registers value A and Q. That is the final product of the particular multiplication. So this example explains how to perform Booth's multiplication. This is the example for multiply 7 into 3. So we know the product value is 21. Using Booth's algorithm, we perform step by step. So first we initialize the register. Here multiplicand is m, multiplier is 3. So equivalent binary value is written here. Then I already told the accumulator and the q minus 1 register initial value is 0. So here we take 4 bits. So the count is 4. When the count is reaches 0, each iteration reduces the count. When it is reaches 0, we stop the particular steps. So this is the example explains the Booth's algorithm in detail. Before performing these steps, we know if q naught equal to 1 and q minus 1 is equal to 0 means we perform a equal to a minus m. Q naught is equal to 0 and q minus 1 is equal to 1 means we perform a equal to, that is the accumulator equal to a plus m. Then q naught and q minus bit both are same means we didn't perform any operations. But in all steps we perform shift right operations. So here the multiplicand value is m is 7, multiplier value is q. So binary value of 7 is 0, 1, 1, 1. It is the binary coded decimal form. Then binary value of 3 is 0, 0, 1, 1. So a equal to a minus m means to easily perform this operation, b is also equal to a plus 2's complement of m. So a is equal to a minus m is equal to a plus 2's complement of m. So a value I take here 0, 0, 0, 0. M value is 7. So 0, 1, 1, 1, 1. So a plus m means to find the 2's complement of m. So to find the 2's complement, invert first. This is the m. So 0, 1, 1, 1. Invert all bits m. So if it is 0 means we invert 1. 1 means 0 like that. So the 1's complement of 0, 1, 1, 1 is equal to 1, 0, 0, 0. Then we add 1 with the 1's complement to get a 2's complement. So after adding 0, 1, 1, 0, 0 and 1. So this is the 2's complement of multiplicand. Suppose a equal to a plus m, simply we perform a value and give the original value of m. If it is a equal to a minus m means we perform a plus 2's complement of m. A is equal to a plus m means we add the multiplicand value with the accumulator. So now we perform the steps in detail. So first a is the accumulator, q is the multiplier and q minus 1 register, then m is the multiplicand. These are the initial values for a, q, q minus 1 and m. So first iteration, first cycle, we store all the initial value here 0, 0, 0, 0, 0, 1, 1 and 0, 0, 1, 1, 1. Next we will check the q and q minus 1 value. So LSB bit of q is 1. Then q minus 1 register value is 0. So if it is 1, 0. So 1, 0 means we perform a equal to a minus m. So 0, 0, 0 is a accumulator value and m. A equal to a minus m. We already found the 2's complement of m. So 2's complement of m is 1, 0, 0, 1. Now we add 1, 0, 0 and 1. So after performing this operation, we perform shift right. So in that, we maintain the sign bit in the same position. So here I write 1. Then shift right each bit in by 1. So here just write 1 is here, 0, 0 and this one shifted here. and the 0 here, 0, 1, again this 1 shifted here. So now again check the Q0 and Q minus 1 bit value. So here this is 1 and 1. So if it is the same bit 1 1 means we didn't perform any operation, but we perform shift right. So again shift right. So if the sign bit here, then shift right 1 1 0 and 0 1 0 0 1. So multiplicand but this remains same in all the steps. So now again we check the Q and Q minus 1 value. So 0 1. So 0 1 means we perform A equal to A plus M. So here accumulator value, we store the accumulator value here 1 1 1 1 0. Now A value is 1 1 1 0 and M. So this is the original value of M. So here I write 0 1 1 1. So after adding I got the value 1 0 1 1 0, then carry 1, then 1 1 0, we get 1 carry. Don't take carry value. So again store 0 1 0 1 here. After performing this operation, we perform shift right. So again sign bit is kept here and 0 1 0, this one move here and 0 1 0 0. Now we will check the Q0 bit and Q minus 1. Both are same, so we didn't perform any operations, but shift right. So 0, then 0 0 1 0 1 0 1, then 0. So our n value is 4 bits, so we stop here in the fourth cycle. Now we concatenated or combined the values A and Q. So our product value is 0 0 0 1 0 1 0 1. This is the equivalent decimal value 21. If you are converting your binary value into the decimal value, we got 21 as the result. Another one example. Previous example, we use both positive value. Here, minus 7 is the negative value. 3 is a positive value. Here also we got the same product value, that is 21. But here the multiplicand value is minus 7. So we take the 2's complement value as the 2's complement of the 7 as the multiplicand value. So 7 equivalent binary value is 0 1 1 1. After take minus 7, it represented. We know how to find the 2's complement. Invert that bits into 1 0 0 0. Then we add 1. So we finally got the value 1 0 0 1 is the binary value of minus 7. And 3 in binary. So we write 0 0 1 1. The steps are same as the previous example. So A equal to 0, accumulator value is 0, Q value is multiplier value is 3, Q minus 1 bit is initialized to 0, and M is the original value of 7 is 0 1 1 1. So it is a negative value. So we take the 2's complement of that value. So this is the multiplicand value. Then follow the previous example steps to perform this example also. Finally, we got this value 1 1 1 0 1 0 1 1. So this is the product value. So initially we convert 7 value into the equivalent 2's complement value. So if you are putting or calculating the value 2 power 0 like that, you didn't get the correct answer. So to get a correct answer, find the 2's complement for the product. For example, here we got the value 1 1 1 0 1 0 1 1. So to convert into 2's complement, invert all the bits 1 0 0 0 1 0 1 0 0, then add with 1. So finally we got the value 0 0 0 1 0 1 0 1, the base 2. We convert equivalent decimal value, we got 21. Thank you for watching.